Welcome from my side. Thank you, Dr. Lee, for the introduction, and thank you for taking away already a lot of explanation I would have to do in my presentation. I will talk about the advanced model-based battery lifetime prediction for vehicle fleets. For those who don't know us, AVL, we are a company based in Graz, founded in 1948 with around about 11,000 employees, spending quite a lot of money on R&D with a global footprint. We are serving three different disciplines under our roof. We are doing engineering service for automotive and mobility industry. We do have instrumentation and test systems, test beds, measurement devices, combined with software and simulation tools that we supply to our customers in the mobility and the automotive world. And we are always looking beyond the limits of technology. So we are dealing with electrification in the automotive industry, ADAS and AD, the zero impact emission where we are coming from, and vehicle engineering and data intelligence, which is my part of the business. To our global footprint, we have engineering and sales centers around the world, headquartered in Graz. We have a very strong presence also here in the US. Also, my colleagues are here on the booth in the exhibition. Why we are talking in the automotive industry about battery lifetime? Already explained several times in this conference, it's all about the remaining useful lifetime of battery. And at the beginning of the life, we are very much focusing on what is the performance and how can I secure safety for long life batteries. In the first life, our customers or the customers of our customers are interested in what is my SOH, how long can I drive my car, what is the best operating strategy to come from A to B, and how does the driving style influence the lifetime of my vehicle, of my battery. In the second life, it's then very much about, should I reuse or recycle the battery? Could I implement another application, or can I sell my battery for reuse? And then, for sure, what we want to avoid is the failure case. So we need to know quite safely when the battery is dead. All of this is a circular economy, and we need to take care about second life and end of life already in development of the vehicle, so to ensure second life and reuse of our batteries. If I go one step deeper in this process, we are in the automotive industry very much focusing on this V process, from developing, validating, and producing vehicles and bringing them in use and then controlling the fleets that are out there in the market. Starting there from simulation up to the final prototypes vehicles, testing fleets, and then the in-use fleets for all kinds of mobility application, passenger cars, two-wheelers, racing, heavy-duty, non-road equipment, also ships. We have on the booth also an airplane equipped with battery electric propulsion, and also stationary equipments. Today, I will give you an overview of what we provide to our customers and what the needs of our customers are that are also influencing you in the development of batteries and cells. So I will focus on the lab topics and then also on the in-use and fleet topics. So why are our customers interested in testing cells and battery? Because still in an automotive powertrain, the battery is the most expensive component of the whole powertrain. So they need to take care that this component lives as long as possible, no added costs to the customers. Although, and if in the battery, the cell, again, is the biggest part of costs. Although costs are decreasing, recently we heard costs have been rising again, so no prediction in the future. I think it will go down again. What are the tasks the development engineers in the electrification area in automotive are doing. The one thing is they need to select the best cell for their application, to validate what the cell suppliers are giving them, especially validating this in areas standard tests do not cover. The question was already before asked, do you do different set points? I will give you an answer to that one. For simulation, yes, we need to bring back the parameters to the simulation models. We need to do system simulations and need to get the model parameters. Our customers need to understand and prevent aging as good as possible in the way they design the system or the pack and the module then. And we need to design battery management software to really operate the vehicle in a good shape and according to the application. And all in these different stages, we generate a lot of data with different purposes, and we need to find a way to reuse this data as good as possible. And that's why we apply data analytics for reusing data, cross-learning, and implement data intelligence. There are several standards in the world for battery testing, and there is no dedicated standard for the automotive industry, but people usually test their battery, and we have seen this already in the presentation before, by this IEC 62660, performing cell performance tests. But what our customers are doing, they combine these tests in different manners. And it's very specific to the customer need, to the DVB, so to the verification plan they run. They try to mimic somehow the real-world behavior of the vehicle, different temperatures, different C rates, different humidity, driving conditions. And they do this large scale. So we are not talking about a laboratory running 10 to 15 cells. They run cells, 4,000, 5,000, 6,000 cells at the time to do these validation purposes. Where, on the other hand, on the pack and module test, they run 10 to 20 units for one generation of their battery. And the biggest challenge is to know how the users are using the vehicle, the product they are developing at the end of the day. Where are they driving? What are the temperature differences? This is a very simple example. Over 3 years of temperature rise and falls, the vehicle sees in a standard life cycle. On the right-hand side, you see a driving cycle with charging, recuperation, driving, load on top of it. This is one single drive that is recorded here. And the question is, what are the real conditions the battery pack is operated in? So, I said already, we apply data intelligence and data analytics to this topic and bring there several steps in the process. To do this, we have developed a platform based on our engineering know-how. We add on analytics methods, very much driven from our engineering projects with our customers. And what we also do, especially for this validation fleet test, is the integration know-how in the one hand side, in the battery management systems of our customers, on the other hand side, in the data collection. Let me phrase it, the data analytics platform. It's a very generic concept. Since we have seen dealing with different topics in the field, we try to gather data from the different environments, starting from simulation up to in use, not only for battery, but for all other components in the field. Bring this in a central location, the central platform, do data crunching, and then basic idea is not already at the beginning separating test and result to a dedicated application, but do this at the end. So independent of the test that is running at the front, in the different environments, we generate the same results for the end user. The platform itself is a web-based platform with a lot of calculation capabilities in the background. With that data harmonization, so we are talking about tons of data, different data formats we need to deal with. And this is also a common problem for our customers. They are not generating all the data on their own. They get data from other people, from other parties, and they do need to do automation and reporting. So what can the data platform do in a similar step? Just for cell, module, and pack, independent on the unit under test, we can do aging behavior analysis, cross components, across unit under tests, with standardized analytics for the main use cases, cell selection, simulation, model parameterization, module pack and design validation, to bring all this data together. If you look to the fleet, I said the main problem for our customers is to know what they should test and how they should test, and how they should define these test cycles we have seen here on the left-hand side. So what are the temperature ranges? What are the C rates they need to apply? For this, we very much focus on these validation fleets. We look into the real usage of the data from the validation fleets that are running out there, but also from the in-use fleets. Bring this data, so the metadata of the vehicles combined with the time series measurement data into the platform. Apply always the same analytics, again, independent on the use case, independent on the test scenario they are driving, to extract, for example, driving, charging, recuperation, braking events, and store these aggregated results in a data store, which then allows us to do analysis on operating regimes. So what is, for example, the temperature ranges we are running in? What are the different SOC stages or SOC rates? And what is the voltage current profile to this? What is the loading profile? How often does the customer load, at which stages? When we have all of these aggregates, and if we have all of these characteristic values, we can use them to fit response surface models. And this is now a response surface model, not really using the raw data, the time series measurement, but this aggregated data, which makes it the first time possible to build a response surface model over a complete vehicle fleet and get the influencing factors, for example, for SOH. So that at the end of the day, we can then later on start to use this knowledge and design, we call it a real-life parametric aging tests. A way to combine real-world drives in the laboratory and get better aging results, more realistic test cases than the standard performance test cases we have seen before. This is the first step. The second step is then how do we bring this to a BMS system? And Dr. Lee already explained quite well that there are a lot of different methodologies. So we gather the data from the vehicles together with metadata to also classify the data afterwards. Bring this in the time series data, and for the modeling part, we mainly focus on HV battery parameters from back and module, like current, voltage, temperature, but also from information we get from the BMS system, because every BMS system is doing already SOH prediction. And we want to reuse this in the two use cases, the state of health estimation and prediction in the cloud, and the other one, the state of health prediction on the edge. Calculate things and make this visualize these results. I talked already about the first point, and now I will give you more insight on this lifetime prediction and what are our efforts there to really support these topics. Already explained before, I have historic data. I know some parts of the battery degradation, but what I want to know is when do I reach my end of life, or when does my battery not perform anymore in the way it does. In a presentation I heard yesterday, people told, yeah, it's a lot of data, and we are really thinking about, since we are also developing algorithms for battery management systems and the controllers that are run there, how can we minimize the data? And for this, we use a two-stage approach. So we do a feature selection as also explained before, based on the field data we have, train our cell models, transfer the weights back to the weight, train again a field model, and go this loop. And since a lot of the BMS suppliers in the field are third-party companies which supply to different OEMs, there's an additional problem. There are knowledge silos or there are IP silos. So our customers don't want to share their IP. And we have found a way how we can do this in a multi-level step, doing fleet-wise estimation, but generating a centralized global optimization over these different fleets without sharing the raw data between the different fleets and the central model, and bringing back the parameters to the local optimization and then to the vehicles. Not going into too much details, we use a concept also presented before based on long short-term memory and the encoder-decoder architecture to really only use the proper features and the aggregates. So our platform itself supports the different use cases in the field, in the laboratory, also for manufacturing, and simulation to bring in the simulation models and enable fast updates and accelerated development for speed and quality. We applied this in different customer projects for passenger cars, trucks, and two-wheelers with huge in-use fleets for system validation and series development, deployed this and operated this on global vehicle fleets, and our customers managed to realize savings worth millions of euros. I said the platform is a generic one, and you may ask the question why. It's not only the battery. There are a lot of components in an electrical vehicle, from e-motor to inverter to power electronics to the transmission parts. These are combined in subsystems like the back, combined with control units again, thermal management and thermal systems, e-drive unit, and the electrical system, and for some cases also the IC, then in the final system. And our platform enables independent on the test case, independent of the component subsystem or system, to generate or transform data streams into engineering insights to make decisions faster. What are the key benefits we get back from our customers and we see? On the one hand side, improved operation strategy and utilization for driving, charging, and parking. A better overall system understanding to avoid errors in operation already early in the development because we get the feedback from the field. Reduction of cost, and last but not least, a valuable input for the next battery generation system, because while you are driving the vehicles, our customers are already working on the next generation of the vehicle systems and need this input and take this input to develop the next better product. With this, I'm at the end, open for questions, and I say thank you.
All right, thank you very much. Are there any questions? Maybe I can start with a question. A very interesting talk. I think it's a very interesting insight from the industry side. So I have shown something from the academic, and this is the industry side. So what is your, I think you have mentioned on one slide how we can generate more realistic data in the lab with combining some field data. The problem I see there is if we age the battery with few data, it will be very slow.
Yes.
Right?
Yep.
We need to age 10 years until we have the data. What's your opinion on this?
So yeah, we know this, and this is also a main challenge or challenge of our customers. And not in the presentation, but we have also methodologies to do design of experiments and intelligence online design in a way that we can shorten the time of these experiments with the same result. Maybe in the next presentation we will come up with.
You mean using some prediction method, maybe? So
yes,
test shortly and predict
exactly.
the future.
Yes,
yeah,
yes.
That's interesting.
Got a question. Hi, Julia Preger, Sandian National Labs. Thank you for the presentation. It sounds like you're getting data from these fielded systems at the BMS level. You're not getting the individual cell level data. It's all aggregated by the BMS provided by the manufacturer, and you don't have any lower level insight. Have you found that getting data at that BMS level is still enough to generate significant insight, or would there be additional advantages, analyses, if you had access to the lower level data?
So two-level answer. In the validation fleet itself, we have instrumentation, so we do get a lot of data on top of BMS system. If we're in the fleet, I mean, cost, our money is everything. Instrumentation is as low as possible. So all the algorithms out there need to deal with the data BMS systems are delivering. This data amount is growing, and as was also presented before, there are more virtual sensors, there are more data coming into, but we as an engineering supplier, we need to work with what our customers are giving us. But I guess this will increase also with decreasing costs of storage and other things.
All right.
Hi, Noel from Lightens in Toronto. Interesting presentation. Quick question. Is the fleet broadcasting data to the cloud in real time?
Yes and no. So depending on the OEM, some are broadcasting in more or less real time, maybe every minute, maybe 10 minutes. Some are transferring the data when they are in the workshop, which is worst case. Yeah, different strategies, very, very dependent on the OEM that is operating it. Not in the passenger car area, if you talk non-road, if you talk agriculture, this is much more common. So they broadcast a lot of data already real time.
All right. Yeah.
Hi, Meredith Wagner, TA Power Solutions. Thank you so much for the talk. It was really interesting. In one of your slides, you were mentioning kind of like a feedback loop, which I sort of interpreted to mean potentially talking back to systems in the field, doing firmware updates based on optimizations. Is your company doing the like controls development as well, or is that like in partnership with the OEMs or?
We do have in our own controls development department organization in Germany, and they plug into the mainstream control unit suppliers. Okay. So we develop models, algorithms on top of this. So we are not also not caring about the way back. This is something the base architecture gives us.
Okay. Usually. Yeah. Thank you.
All right. I think we still have some time. Maybe last question from my side. So you see, there's no additional cost for the OEMs to collect data. I mean, hardware side, but they need to, storage it and communication. That costs money. Yes. Right. So how can you convince them for such, aging prediction on optimization, because it really needs a long time to show, okay, we have some benefits, we can earn money, we can make it safer. So how can you do that?
That's a good question, but most of the OEMs do have some kind of strategy to gather this data. So it's really not we need to convince someone. They come to us asking for services, helping them to go that way. That's very much the engineering part of the business. We then need to convince them on based on our algorithms capabilities, but data collection is a common sense in the industry.
Yeah, I totally agree, because safety problems very easy to convince,
Yes.
but aging is a quite long term, right? So, all right, thank you so much for the interesting talk.